All right, thank you. Hey, welcome everybody. My name is Stephen Robinson. I'm the lead architect for the E-Core line. I'm an Intel fellow. And here today, we're going to talk to you about SkyMont, the next generation E-Core. Thank you very much. OK, so we had a couple of goals that we set out when we wanted to do our next microarchitecture. One of the key goals that we had was, let's take the low power island that was introduced in Meteor Lake in Crestmont, the Crestmont low power E-Core, and let's see how we can use that to get more battery life, let's get more energy efficiency, and let's get PCs that last longer. So our key approach was to maximize what you can run on the low power island. Running on the low power island comes from a lower cost. It has an efficient compute. So the more workloads that we can run on that low power island, the more your battery life is going to get better. So that was our goal. You know, the next thing was making sure we can run a variety of content. So every day, there's more software, there's more vector, there's more general software that uses vector instructions, things like that. So we took a goal and we said, hey, we're going to double our vector capabilities, and we're going to do it in a balanced machine and make sure there aren't too many bottlenecks. So that was the second thing. And you know, AI is a part of that. Most AI workloads use vector instructions. So that was our focus. Third is scalability. So the way you've seen Intel embrace hybrid computing is we can have P-cores, we have E-cores, and we can scale out with more E-cores. This gives you a way to scale out efficiently. That's underneath power constraints, as well as cost-wise. You have plenty of, you can put more E-cores into an area. So that was the third, is we wanted to make sure that we continued to have scalability. So that was our third vector. So I'm excited to show you how far we've come. So now I'm going to talk about the specifics of the microarchitecture. So every modern CPU microarchitecture starts with branch prediction. Branch prediction, these are instructions. Where are you going? Turn-by-turn instructions. The branch predictor tells you turn left, turn right, 200, 400 meters. That's what branch prediction is. So in SkyMont, we, of course, made it a little bit larger. But more importantly, we started scanning more data reliably. So in the Crestmont E-Core in Meteor Lake, we moved to what we called 128-byte prediction, which means we'd scan across 128 bytes looking for the next taken branch. That's the next instruction in your turn-by-turn instructions. On SkyMont, we fixed some things to make it more reliable. So in Crestmont, we had to start at a specific boundary, 128-byte boundary. Sometimes we only got half of that. Sometimes we only got a quarter of that. On SkyMont, it's arbitrary. You can start at any 64-byte boundary. We call this even odd. Now, no matter where you start, in which cache line, you can look across more. And fundamentally, we're just getting that next instruction quicker. This helps us fetch the data faster as well. So because we know where we're going, we can start the access. So if we're going to miss the cache, if we're going to get the data out of the cache and send it to the rest of the machine, now we can do that a little bit quicker and more reliably. Here, we can get up to 96 instruction bytes. So it's not 96 instructions, it's 96 bytes that can produce instructions. Remember, x86 is a variable length instruction ISA, which means there's any number. It could be 96, it could be fewer than that. So we can grab 96 bytes every cycle, and we can load that into some buffering before we send it to our decoders. Those are 50% deeper as well. So now that we can fetch the data, or we can predict it, we can fetch it, now we hand it to decode. So several generations ago, we introduced the industry to clustered decode. So we did this on Tremont, we did it in Gracemont, we have it in Crestmont. What this is 2 independent 3-wide decoders. So each one can find up to 3 x86 instructions, again, variable length. And here, we can do that previously on 2 clusters at a time. In SkyMont, we add a third cluster. So now we've improved our instruction throughput for decode by 50%. This is a 9-wide front end for sustained decode. The first time we did it, we thought it was a pretty good idea. We've learned a lot. We've optimized it. We've made it more efficient. And here, this kind of shows you that we've gotten good enough at building it that scaling out to 9-wide isn't this massive area impact. It's not this massive timing impact. It's actually quite efficient. So, we feel strongly that any industry debate about x86, variable length instructions, it's done. We built it. It's good. Now, what other problems are we optimizing? What other problems did we run into? So one thing that happens is sometimes in x86 and in other ICEs as well, you end up generating multiple UOPs for a single instruction. So in Intel, this is microcode. We have a microcode sequencer. It's a ROM. It fetches, it decodes into multiple instructions. So when we introduced cluster decoding, one thing was that we could only access the microcode ROM one at a time. So if one cluster wanted to get the ROM, it would wait, and it would get its turn. It would go to the ROM. It would fetch the instructions. So this was basically serialization. So what we've done in SkyMont is we've introduced what we call nanocode. So microcode, nanocode. Nanocode is where we put decoders in the clusters that can generate UOPs for common and specific microcode flows. So what this does is this allows us to continue doing that decoding in parallel. Take a gather instruction or something along those lines that we would have to generate 2, 3, 10 UOPs. Now, cluster 0 can happily generate gather UOPs. Cluster 1 can also generate gather UOPs if that's what it's doing. And cluster 2 continues decoding whatever it wants out of order. So nanocode is that next thing that kind of adds to the bandwidth and gets more reliable decode. Finally, with our cluster decode scheme, again, it's replication. So what that means is when we replicate it, we replicate the resources that go with it. So, earlier I talked about 96-byte fetch. That's because we'll do 32-byte per cluster. So it naturally scaled out. The same thing is true for the queue that goes between the front end of our machine and the back end, the UOP queue. So in this case, because we added a third cluster, now we have 50% more UOP buffering between the front end and the back end to help smooth out performance. So we've got a 9-wide front end. What did we do in the back end? So going from the front end to the back end, if you look at Gracemont, that was our original Lunar Lake E core. It was a 5-wide microarchitecture. We could allocate 5 things per cycle. In Gracemont, in Meteor Lake, it's 6-wide. So in SkyMont, again, 9-wide front end, we went to 8-wide allocation. So SkyMont, the E core in Lunar Lake, can allocate 8 UOPs per cycle into the back end of the machine. We also done our retirement. Previously, we would retire up to 8 UOPs per cycle. Now we'll do 16 UOPs per cycle for retirement. What does this mean? Essentially, it's not necessarily directly correlated to performance, but it frees up resources. The faster we can retire, the more resources we can free up, and the more efficient our machine can be. Right? We could overbuild things and have slower retirement, or we could build wire to retirement and make some of our queues a little bit shallower, and that saves area in C9. So this is what we did. Okay, the third one, in a perfect microarchitecture, you would end up with what we call the critical dependency chain. So I have one instruction that feeds another instruction that feeds another instruction, and in the end, with infinite resources, you find that dependency chain. So here, we've continued innovating and having more ways to actually break that dependency. So even though 2 instructions appear to be dependent, we can know that we can get the data from somewhere else. A classic example would be a 0 detection, an idiom. You have an instruction that you know will produce a 0. So that's one example of breaking a dependency. We have more. We have cases where we will take a load that we predict is going to forward from a store, and here We know of that connection, so we don't actually feed the load data to the dependent UOP. We can feed the previous store data. Another example, in x86, we have been doing ESP folding, where we take the stack pointer and we kind of accumulate the offset. We can do that in more cases now as well. So that's the dependency breaking. This short circuits the dependency chain and gets more IPC, more performance. And it does it in a very efficient way because we're breaking dependencies. We don't have to wait as long. So that's our out-of-order engine. So now that we have 9-wide front end, we have an 8-wide allocation, 16-wide retire, we grew the out-of-order window. So if you look, again, at the E-core and Alder Lake and Raptor Lake, that was 256 entry out of order. You look at Crestmont, we actually left it the same. For Crestmont, we said, hey, let's add a few more resources, let's balance the machine. In Skymont, we're about 60% deeper. So here we have a 416 entry out of order window. Going along with that, again, there's lots of resources that need to scale up, physical register files, reservation station entries, load and store buffering. All of those are larger in the Skymont microarchitecture. So 8-wide allocation, 400 plus entry ROB. How many dispatch ports? So we're up to 26. That's a pretty big number. Our approach to reservation stations, execution units, instruction scheduling is a little different than some others. So on E-core here, on Skymont, we firmly believe in dedicated functionality produces energy efficiency. So you can share schedulers or you can make them dedicated. You can share execution units or you can let them execute in parallel. So for us, we continue to let them execute in parallel. So here you can see this is the integer stack blown up in the picture. We have 8 integer ALUs, so 8 single cycle operations per clock. We can resolve 3 jumps per cycle. We can execute 3 loads per cycle. The other thing we've done is we've tried to bring symmetry. So we have 4 shifters per clock. We have 2 integer multipliers. You know, in general, more hardware, more parallelism. This is on the integer side. Now here's the other thing. This was one of our design, you know, our fundamental things that we wanted to do. I mentioned vector performance. So previously, for say floating point operations, we had 2 128-bit pipelines. So here, as table stakes are part of our plan, we wanted to make sure that we were industry competitive. So we doubled that. So now we have 4 128-bit floating point pipelines. We had 3 integer SALUs previously, and now we have a 4th. So again, being consistent with that, you know, parallel where we can be, consistent port binding, consistent amount of ALUs, that's what we have here. So what this does is our theoretical peak, tops, flops, however you want to count it, is 2x the previous gen for these types of workloads. In addition, we cut latency. So FAD, FMOL, FMA. We're down to a 4-cycle FMA, which is pretty consistent with modern microarchitectures. You know, we have more bandwidth, but shorter latency at the same time in Skymont. Native hardware rounding support, floating point normalization. So previously in Gracemont, Crestmont, we didn't pay for that hardware. So, you know, let's say I have a program, C code, I compile it, GCC, I say -02, I think I'm optimizing it. When you get that binary, anything is going to follow strict IEEE rules because they don't know if you are or aren't going to need that, and they assume that you do. When that happens, sometimes you do a bunch of math and it comes out to a number that you can't properly represent in floating point. And so there are rules on how you format that. DAS, FTZ, these are flags in x86 that give you a predictable answer, but it's not necessarily following all the rules. So when you're not doing that, which a GCC02 compile does not do, sometimes we would go to microcode and we would say, please help, please fix this value up for me. We get rid of that in SkyMont. We now reliably take care of all of that in hardware. So this is just an example of something that you didn't necessarily notice, but we're trying to make sure we clean up some of those glass jaws and give you that reliable performance. The other thing is, AI. Those of you in this room skipped the AI talk next door, but you get to do it later. So here, clearly we have more execution units. So VNNI, these are in our SI-mole execution unit. So we have 2 more of these. In Gracemont, we had 1 SI-mole. In Crestmont, we have 2 SI-moles. And in Skymont, we have 4 SI-moles. So in those 2 generations, we've quadrupled the amount of hardware you can use for VNNI-like instructions. And again, if you're doing FP32, FP64, again, we have 2x on those as well. So adding the vector hardware is a piece of it, but you have to make sure you try to balance the rest of the machine. So this is the load store. This is the L1 data cache. We have gone from 2 loads per cycle to 3 loads per cycle. We continue to have that 128-bit, 16-byte data path. This is the match for vector. So now we're up to 3 loads. So this is 50% more L1 load bandwidth. There's a 3rd load address generation unit that goes with that. And on the store side, we doubled our store agens. So now we have 4 store agens per clock. Our peak store throughput is 2 per clock, but for address generation, it's 4. We do this so that we can resolve store addresses. This speeds up loads. This gets rid of cases where we fail to predict that the store and load aren't connected. It's just general performance goodness. So that leads to faster unknown store resolution. And then on our shared 2nd level TLB, this is for both code and data. On Gracemont, it was 2,000 entries. On Crestmont, it's 3,000 entries. And now in Skymont, it's 4,000 entries. And we also added more what we call pipeline PMH entries, table walkers, things that look at page tables. We can do more of those in parallel as well. So that's load store. And now we go to our L2. So in Lunar Lake, we have a 4-core module that shares a 4 megabyte L2. If you look at Crestmont in Meteor Lake on the low power island, so there were two types of Crestmonts in Meteor Lake. There was one 4-core module that was on the ring that had a 2 meg L2, and that shared that LLC with the P cores, with Redwood Cove. In the low power island, it was isolated. It wasn't on that LLC. It wasn't on that ring. And that had a 2 megabyte L2, and it was a 2-core cache. So here's where Lunar Lake gets pretty interesting. Lunar Lake doubles that core count. It doubles the L2. So we went out of our way to try to improve that core count scaling. So when I go from 1 core active to 2 cores active to 3 and 4 cores active, we wanted to provide more bandwidth. So we doubled our L2 bandwidth that we have available. Each core can bring in a single cache line per clock, but our L2 can produce 2 cache lines per clock so that it helps with that parallelism for multi-core workloads. We also improved our eviction data path width. We were 16 bytes per clock previously, and now we're 32 bytes per clock. Again, just getting better at memory transfers, memory bandwidth. The other thing was, this is kind of fun. Some of you out there, Tech Press, you benchmark our cores, you run micros, and you notice things. And some of you noticed something, right? When we have data where multiple cores in the same module want to use it at the same time, and specifically when one core has modified data and it's still in the 1st level cache, and another core wants to access it, we do a funny thing. We don't say, here's the data, we can execute it. And this is Gracemont and Crestmont. What we do is we pretend like it misses the L2. We send it to the fabric comes back and asks us for the data, we provide the data to the fabric gives it back to us. So suddenly people were surprised, hey, the data is near and the latency is high. In fact, the latency was a little bit longer than a normal cache hit, and that's because of this sort of round trip behavior. So it was nice if you guys. But the good news here is we went ahead and fixed it. So here in Skymont, we have what we call L1 to L1 transfers. What this means is that when one core asks the L2 for the data. We see that it is resident in another core. And we don't go to the fabric anymore. The L2 goes and says, hey, please give me the data. It grabs the data, provides it to the core locally. The fabric isn't involved anymore. This is more reliable performance for the cases where people have really tight pipelines and they're sharing data within a module in local time space. So that's more reliable latency for cooperative workloads. So, hybrid at Intel, we've got two slightly different usages, and Meteor Lake is a great example of that. Again, we had Crestmonts on the ring, on that shared LLC, and we had Crestmonts in the low power island. Here in Lunar Lake, we're going to focus on the low power island because this is where we have put the E-cores. You know, again, as I mentioned to begin with, our goal is to run as many workloads as we can on that because the low power island, as you heard in the keynote, in the Q&A, right? We're not running a ring, we're not running a P-core, we're close to memory. We have now a system cache, a memory side cache. So that's also new versus Meteor Lake. So now we have more cache and we can be power efficient. We still have the ability to use the E-cores on a compute tile, on a ring, on a fabric, on an LLC. In Lunar Lake, that's not the discussion, but I do mention that we still have that ability for SkyMont, the core itself. So let's go into the low power island, and let's focus on this particular usage. So I'm going to show you a comparison of the Crestmont LPE core in Meteor Lake against the SkyMont LPE core in Lunar Lake. Here's the performance. This is IPC. So this is SpecInt estimated. This is a generic GCC02 compiler. This isn't a custom compiler. This isn't a binary that's been optimized specifically for one versus the other. This is the exact same binary. And here you go. So on the integer side, it's a 38% geo-mean IPC uplift. You can see the S-curve behind it. That's each subcomponent ordered by performance. There's no negative outliers here. And you can see that it's not one or two workloads pulling it up. It's a nice easy S-curve. On the right side is floating point, so SpecF. I mentioned we doubled the vector hardware. I mentioned that we actually fixed some denormal issues on floating point, which does affect this, so that is included in this data. And here we get this 68% IPC uplift. So for SpecFP, so if you're vector-ish AI workloads, this is the type of thing that could be a good proxy. And again, everything on the right is positive, no negative regressions. So that's IPC. Let's look at power and performance. So here's power and performance. This is a single-threaded view. So this is a single SkyMont E-core in the Lunar Lake low power island against a single Crestmont LPE core in the SoC die in Meteor Lake. 1/3 the power at the same peak performance of the previous generation. So full frequency that we chose to run that at, same power, 1/3, 0.3. 2/3 less. At the same power level, 1.7x the performance. And then peak to peak, this is where Lunar Lake gets really interesting. The power delivery and flexibility of voltage is a little bit different in Lunar Lake. So now we have the option to run the E-cores a bit faster than we chose to run them in Meteor Lake. So they run them not just with the IPC advantage, but also with the frequency advantage. And here, peak to peak, 2x. Now that's ST. I mentioned we've got more caches, more bandwidth, and we doubled the core count. So let's look at MT. Here, I'm comparing 2 cores against 4. So this isn't ISO work. But this is power perf. Again, 1/3 the power for the same peak performance. So running those 2 LPE cores in Meteor Lake at their full frequency. We're 1/3 the power for the same performance. Now we're 2.9x the performance at the same power, and we're 4x peak to peak. So the the low power island in Lunar Lake literally has 4x the capability as a low power E-core cluster in in Meteor Lake. So when I talk about coverage, this is exactly what I mean. If you look at Meteor Lake and you do video playback, Netflix, some of these things, something that's very low CPU overhead, we were able to catch that work on those low power E-cores. But if you do something more interesting, Teams, multi-directional video playback, conferencing, it tends to fall off. Those cores don't quite provide enough performance to guarantee the work can stay on those cores. So we fire up compute tile, et cetera. Here, we should be able to capture those workloads very well on the E-cores. Later, you can listen to the thread director talk, and we'll tell you exactly how we help the software system make sure that it does that work and gets the right efficient point. But this is what I mean about coverage. This is key to Lunar Lake battery life. We can run more workloads in a lower power environment on a lower power core with fewer things turned on and still give you great user experience. So that's SkyMont E-core in Lunar Lake. So I also mentioned that we'll have one on a ring, on a fabric. This is not Lunar Lake. This is, again, just to talk about what the capabilities of the IP are. So I'm going to do a little bit different comparison than I just did. What I just did is I compared against the previous generation CCG product, Meteor Lake, LPE core to LPE core. So here, I'm going to compare against Raptor Cove in Raptor Lake. So today, Intel's primary desktop product that we ship is Raptor Lake with Raptor Cove as the P-core. So let's see how we do. This is IPC. This isn't peak performance. This isn't frequency. Raptor Cove runs at 6+ gigahertz, right? Absolutely amazing. Wonderful core. SkyMont, we're not trying to run at 6 gigahertz. This is not the goal. But this is IPC. Again, this is the same workload that I've shown you for all of these. This is GCC, spec 17 estimated, compiled 02 out of the box. 2% higher on int, 2% higher on FP. Now before I said, when comparing against E-core, that it was all positive, there were no negatives. Here, it's a trade-off. Here's an S-curve. You can see there are a few below the line. You can see there are a few above the line. So I don't mean to tell you that all workloads are 2% faster in IPC on this IP. It's a little bit of trade-off. But fundamentally, GeoMean, spec int, and spec FP, 2%. So let's map that to power and performance. This is the full peak power and perf curve between the two. This is SkyMont in the Lunar Lake process. That's Raptor Cove in Raptor Cove process. You can see the peak performance is higher. Again, you can scale to 6+ gigahertz. So let's zoom in to kind of power envelopes that are more likely for an E-core or in a low power island. 0.6x the power at the same performance level in that middle of the curve, or 20% higher performance at the same power level. This is what you're getting out of an E-core. This is what you're getting out of SkyMont. This is what we think is key to driving hybrid, to driving PC efficiency, to providing long battery life, and providing a great user experience for Lunar Lake. So these are our goals. More workload coverage, that's the 4x. More things we can run. Double vector and AI, that's the floating point performance that I showed. and scalability. Again, we did this, you guys have, some of you have probably seen the floor plans of Lunar Lake. You can probably find the E-cores. I don't know if we've called them out yet. We didn't break the bank. We can scale that out in general. Thank you. That's SkyMark.